Hey, welcome to the Engineering Bard Show. Today we are doing the Zener Diode and applications of the Zener Diode. We're going to analyze the data sheet. We're going to introduce some formulas. We're going to draw the circuit and do three important problems. I think they're pretty important. We're going to bench test it. There'll be a thank you section and, of course, the signature of my musical outro. Hey, please do not forget to subscribe and hit that channel, hit that like button there. Make sure, and also, if you could leave a comment down, I really would appreciate it. And subscribe to YouTube. Thank you very much. Now we're at the Zener Diode application. So let's go ahead and talk about this for a second. Okay, so Zener diodes are primarily used for DC voltage regulation. They are specially doped to work in reverse bias rather than forward bias. You could still use them as a diode, but that's a waste of a Zener diode since they are more expensive than your normal diode. So they are made out of glass. There's some glass surrounding it, and there's some material in there, so specially made. So some of the key formulas are the change of V over I is ZZ. That is the resistance that's inside the diode. Okay, there's that one right there. So we're going to talk about that a bit. That plays a huge play on trying to figure out the voltage settings. Now there is however, when we get into these components, temperature do have a play on how well these little devices perform. So the temperature, normally these devices are tested at 25 degrees Celsius, but sometimes you may have something where it may be a little bit too cold or too hot. What we're kind of concerned about is when it gets too hot. So if it gets too hot, then more current, and that could definitely throw off. It will change the voltage and the current that's flowing through the device. Down there is the diode that we showed before. Is pretty straightforward. That's just your silicon diode right there. The other one is this one right here. Looks like the Egyptian thing, like kind of. That is the symbol for the. So here we are looking at the Zener diode data sheet, and I showed in the past, it's a pretty small device. It's made out of glass and all that, but there's some parameters that you might want to consider before we go. And there's many different types of Zener diodes depending on your applications of what you want to use it for. So one of the things you have to watch is how much power dissipation it is. So that's right here. Watch out for that. Right about there. Okay. Watch for that. All right, now here are some things that you want to be careful about. Now there are many different part numbers here, and these are the part numbers. So let's go ahead and highlight that real quick for the audience. So let's go ahead and highlight the part number. Okay, that's important. And we must have the Zener, the voltage this is where it regulates. Right here, Zener voltage. We call it VZ. VZ. Okay. And so the test current, which is going to be important, there's IZT and IZK, but it doesn't have it there, but we're going to call it that. That's right here, and that's right here. Those are two columns. Okay, also, now the reverse leakage, that's not that important right now. Don't really worry about, but the ZT, the dynamic resistance, it has a little bit of resistance depending on what you want. And so that is pretty much it. But trust me, that is enough. That is enough. So you see, let's take one for an example. The IN4731A. You see how it's anomalous at 4.3 volts, and it reads. The stats are in columns, and the individual parts are in a row. So 1738 is 4.3. That's nominal. The currents, we're going to talk about that. That's the maximum and minimum currents. That's when it regulates. And the ZZ resistance. That's important. And that should be it. We're also going to talk about the temperature right here. Let me see if I can. Okay, see that? Okay. See that? We're going to talk about that, how that affects the current. So it's pretty important if your Zener diodes are going to go into some very harsh climates. So sometimes very hot climates, there's some your electronics may go into industrial smelting areas where it's like thousands of degrees. You want to make sure that when the temperature goes up, there's more current, and that basically can alter the current, basically mess up the part. Okay, so this is what it sort of looks like. It's 3.3 millimeters. Yep, 26. Yeah. So, okay. We talked on some of the earlier videos there about the silicon diode, how this is the diode curve, and we had to sort of seen the curve, and we're looking at a graph, and this is the reverse. This is reverse bias over here, and this right here is forward. Okay, and we said this was for the silicon diode was like 0.7, 0.5, something like that. So it turns out a long time ago, not quite sure when, the scientists who designed when they were doing a breakdown on the normal diode there, they noticed it hold a voltage right here. The voltage of the diode. It was holding, and then it avalanched. So they created a diode that was able to hold the voltage. So what they created was a Zener diode. It works in the breakdown. So it hangs out right here. So let me erase this. Okay. Let me get this right here. And okay, let me draw it out for you. Got about 1 million pens over here. I went on a pen spending spree because I run out of ink all the darn time. And so the Zener diode, which there we go, hangs out right here, right in that curve. That's where it hangs out. Okay, right at that curve. So it hangs out at the breakdown. So now they figured out that voltage VZ is at whatever value you want. You can have it 5 volts, 6 volts, 10 volts, 12 volts. Some go, I think, 80 volts, something like that. And it holds, however, current is still flowing through this diode. So even though the voltage is sitting at a point, current is still gathering. So you can still burn it up if you put too much voltage in it, but it will regulate at a a Zener at a VZ value. Now let's do a couple problems. I got 3 or 4 problems. Let's do the first one right here. Determine the minimum maximum input voltages that can be regulated by this Zener diode below. I highly recommend you take a screenshot of this. And what we want is basically what's the minimum and the maximum of the voltages that can regulate out of this diode right here. Okay, go ahead and stop the video and try the problem out and then compare the answers. I'll see you there on the board. We got a problem. We have a problem. And what we want to do is find the minimum and find the maximum. So we're trying to find the minimum amount of voltage that will regulate this thing, and we also need to find about what's the maximum amount of voltage coming in that will keep it regulated. Now, before we begin, this is the circuit that we have. However, what we want to do is, before we even tackle this problem, we want to gather up information, kind of like a detective, kind of like a, and we go to the data sheet. We want to find are the important details. So I got this data sheet. You should be able to see it on the right side. I think I should have it like that. But what you want to see is power dissipation. So anywhere around here, our PD equals, it says 1300 milliwatts. Just say 1.3 watts. Whoa. 1.3 watts. Okay, so we got that information. Now we got this diode right here, 1N4733A. That is a 5.1 diode. Okay, so we know that VZ equals 5.1. So that's going to be helpful. Okay, we know that the IZM, it says IZTI, I think we call it IZM, is 49 milliamps, 49. So IZM equals 49 milliamps. Okay, so this is the circuit. I want you guys to make sure we're just gathering information. IZK equals 1 milliamp. Okay, make sure you put the 1 milliamp. Okay, so that should be in the board. I think I got it right this time. And ZZ, which is your resistance, equals 7 ohms. It's on the data sheet. So we gather up information. Okay, now what we want to do is replace this Zener to something that we know. Our Zener is a substitute. The Zener it acts like a battery with a resistor, especially this one. Okay. Plus, minus, acts like a battery. What we're doing is analyzing it. We're analyzing it. The reason why we want to analyze it is because it saves time. Also, we don't need to test it to make sure that it's, we don't want to see how low it goes. I mean, you can do that, but it's just sort of, if you can analyze it, it will basically speed up that process. You don't need to test it onto your bench or anything like that, even though we're going to do that. But this will save a lot of time. Now, we have our governing equations. So over here is square root of V over change of V over change of I equals ZZ. Okay, so the ZZ is a constant. It shouldn't change. It never changes. And of course we have, these are your governing equations. Of course we have Ohm's law, or it's becoming Ohm's rule, but you know, V over R equals I, you know. That's what we know. We're also going to do a KVL loop. So write stuff down. We got our givens. That's going to help us out. And we need to find the min and the max. Right now we're going to find the min, and then later on we're going to find the max. So does everybody see that? I want to make sure I get out of the way, because sometimes I block the way and you guys can't see nothing. So that's what you want to do. Okay, I'm going to erase this because I need room. Okay, find the min, find the minimum voltage. So we know that VZ, what we want, yeah. Is VZ, let's go ahead and focus on this part first. This is, you know, this is first and that's second. So let's go ahead and erase this. Erase this part right here. Okay. And we got VZ minus I2 minus the change. Actually, it's VZ change of I times ZZ minus V out. Okay, so on this circuit right here, V out, okay, let me just make sure I get out of the way. Okay, you guys kind of see that? Okay, I'm going to get in the way now. V out equals VZ minus the change of I times ZZ. Okay, so let's go ahead and erase this. That's our equation. Okay. Is that cool? All right. So now what we want to do is our change of I is right here. It comes in our data sheet. That's the change of I. Is IZM. So basically it's V out equals VZ minus IZM minus IZK times ZZ. Okay? Times ZZ. It's supposed to be times ZZ. I'm going to head and erase this, okay? Because I need room. I write big. ZZ. Okay? So we're just focusing on that little part. That cool? Okay. Now, let's go ahead and now all we got to do now is put in some numbers. And so we substitute these numbers that you see on the right-hand side. So VZ minus 48, 49 minus 1 is 48, okay? 48 milliamps times, actually it's 5.1 minus 48 milliamps times 7. That's the minimum. All right, so I got my handy dandy calculator right here. You know, so let's see. Okay, so everybody, I had times 7. Okay, 5.1 minus the answer. It's 4.764. 4.764. It equals 4.764. So that's the right side. Okay. Okay, we're just about done. Okay, now we want to do this side. This side right here. $125 ohms. Okay, the variable coming in. We're not quite sure what that is. But V in minus V out, V in minus V out, or actually it's V out minus V in, okay, equals R. Okay, so that's sort of, but we need to solve for V in. So we have one, so you have to kind of consider that only, let's say this will take a minimum of 1 milliamp. And that's sort of, so we're putting in the minimum amount. So I times R, so 125 times 001, I do believe is 0.125. That one I kind of did a bit. Okay, so now we add that 0.125. And tell you the truth, even if you just did this part, you would have been okay. Because it doesn't really add that much. $4.889. 4.889 volts. 4.8899 volts is the minimum. Okay, so on the next video, we're going to talk about the maximum. The maximum is a little bit more complicated, but it's doable. So let's go ahead and erase this really quick, and I'm going to put this on the corner, okay? Let's put this on the corner so I don't forget it, especially me. So Vmin equals 4.889 volts. 4.889 volts. Probably the most important one is finding the maximum. It's a little bit more trickier than finding the minimum. Maximum is to see how much voltage, what's the maximum amount of voltage before this thing dysregulates. It doesn't regulate anymore. That's the question. It's a very important one too. So we have a data sheet, and we write everything down. One of the ones that we didn't use was the PD. That's the power maximum. That's the most amount of power. To find the current, so we're going to erase. So we're going to work on this side and then this side. But this side, we're going to erase this side for right now. And we're going to work on this side. However, I1 is coming in. This time I1 is coming in. And it's coming in at a pretty good size amount of current. So PD over VZ. Okay, that's our government. There's one equation. Square change of V over the change of I equals ZZ. Okay, so I want to make sure you guys all see that. I'm going to get out of the way. Okay, and this Zener right here, we're going to take out this. We've already discussed that. It's going to be a resistor with a battery. That's a resistor and a battery. This is VZ, and that's ZZ. Okay, and I1 is coming in this time. So when I1 is coming in, we got PD over V2. PD is, I'm going to say, is also V over I over V. Okay, so I'm going to erase this real well. Yeah, PD over V over I. So let's just put the arrow down. I'm going to go because I don't want to erase that, okay? So that is 1.3 watts over 5.1. 1.3 watts. So these guys are pretty tough, okay? They can handle a lot. Now, it's going to equal 1.3 over 5.1. That's 255. We're going to round it up. 255 milliamps. Remember, the V cancels, and it equals current. Okay, that's why I did that. Okay, so that is very important to understand. So now we have I1. So let's go ahead and put this over here, okay? I1 equals 255 milliamps. Okay. All right. So we got all this current coming in. That's bad news, but that's just the way it is. Now, in here, we got a V out. Same thing as it was before, but this time it's going to be V out equals VZ minus I1 minus the change of I times ZZ. Or actually it's plus, excuse me. We're gonna add it because we're adding the voltage this time. So one thing about the physics is it's coming in. So you got to consider stuff is coming in. It's going to add this. It's going to add more. This is the extreme case. So it's not going to subtract it. If it subtracts it, then it's going to be almost like a few volts. It's going to go the opposite way. It's going to increase the voltage, okay? So you have to consider the physics before the math. Okay, so I1 is, so we got, 5.1 plus up 255. It minuses that, though. That is true. 49, so it's 48 milliamps. We want it consistent now because we had to do that, so it has to be consistent, times ZZ. I times R equals V. We're just trying to find the V out. So let's go ahead and do that. It's all milliamps, so that's milliamps. So it's 255 minus 48, 207 times 0.255 minus 0.048 times 7. It's 1.49. 1.449 plus 5.1 equals, so plus 5.1 equals 6.549 volts. Okay. That is definitely part of the answer, but that is not the answer. So don't put that down. That's only part of the answer. It can handle a lot more than that. Okay, now, but keep that in mind. Keep that in mind. Now we have over here that your V out. So now we have a resistor here. And now we have this 125 times, this is V out plus V in. Now, because we're adding it the worst case. So V out. So this is, wasn't it 255? Yeah, 255. 55 milliamps. So that's plowing through that resistor. Combine that, you get voltage. So 0.255 times 125 equals 31 volts. 31.875 plus 65.49 volts. So that does make a difference. 65.449. 38 volts. Equals 38.4247 volts. Okay. So it's 31 to 38. Okay. So there's a range. 31, I forgot it was 31 through 38. But it is 38. All right, so let's go ahead and erase this. Go ahead and erase this. Do you guys understand that? Do you understand that this V in plus the V out equals the VT, because we're combining everything. It's doing the worst case. Okay, so that V in is you times this by this plus you add this, what I just said. So your V max equals 38.4247. Let's say 43 volts. That makes sense. Just kind of round it up a little bit, and just a fraction of a volt's not going to do a heck of a lot, At least not in this case. That's it. So that right there is a pretty important question, is finding the min and the max, But you can see what I love about this problem, that even though you're getting a min and max, that's still popping out 5.1 volts. And you're going to see that in the lab how tough that is. So they use, in a voltage regulator, even in your cars and all that stuff, they use a Zener diode, plus they use some other, like the MOSFETs and all this stuff, is to regulate that. So the Zener is the main force behind the regulation. And so inside a regulator will always be a Zener diode. Doing a thank you section. I always do a thank you section. I appreciate everyone who watches me. But who watches me the most are my sponsors, and as long as they're entertained, they're happy. YouTube, I'm afraid you're number 2. But I want to thank YouTube for letting me use your platform as sort of a sounding board. Now, career in YouTube was not my first choice. Now I'm gonna be vulnerable out there for people who are. I am 50 years old. I'm 51 actually, and I just want to let people know that things are different in the market, and career YouTube was not my first choice. In fact, it wasn't even my 5th choice. In fact, I don't even think it was my 10th choice. I've been doing YouTube since 2014, but more of a hobby, kind of a joke, kind of serious. And I did this channel not because of money. I'm not doing it because of money. I'm not doing it because of fame. I'm doing it because I believe that the school didn't do a good job. The university didn't do a good job, and they don't do and we pay a lot of money. Students pay a lot of money to get educated. And when they go out in the world, when they go out in the world, the engineering companies and stuff like that, they're not in good moods. They're not in good. I don't know what happened. I'm not quite sure, but America's in a bad mood right now. So me, being sort of a class clown that I've always have been, I'm here to try to get you guys in a good mood and just enjoy what you know. And we're just going to go through 3 topics that I like the most, which is digital, Arduino coding, Arduino code. We may go beyond that, but I doubt it. There's a lot of topics out there. The prospects for engineers finding jobs is not good. I mean, they only hire the best of the best, and when they do hire the best, they're pretty disappointed. So my job is to uncover knowledges that may not was taught. That nobody knows everything unless they're exposed to it. So so that's what we're doing, and YouTube's been great. They've been they've been great. They've been quite supportive. Thank you, and watch the next section, and just have a good time. Thank you very much.